Good morning, everybody. Thanks for coming to the Watershed Alliance breakfast. Sorry we opened a minute late, but here we are and excited to have a great session this morning.
So if you're joining, feel free to introduce yourself in the chat box. Make sure the drop-down menu is clicked to panelists and attendees in the chat box so everyone can see who's here. If you want to let us know who you are, where you're zooming in from this morning. We've got 42 people on so far. I know we can see that, but not everyone can see that. So we've got a really nice crowd already here.
You know, Laura Heedy always talks to us about amphibians at this time of year. And as a hydrogeologist and somebody who thinks about vernal pools just as a structure, I was thinking about the geologic forces that create closed depressions. Weathering patterns don't do that, right? Streams always create a downcut and therefore an outlet. So what is it that causes closed depressions? And there are actually only a few geologic activities that create closed depressions. I'll let you think about that for a moment. One is land settling. One is slope failures, where you have a little landslide and then you end up with rumpled topography. But the dominant one in our geography is glaciers. The glaciers, you know, we were covered by a mile of ice, and that big sanding machine created a topography that left closed depressions, both because of the underside of the ice, and also because as the ice left, it left piles of debris everywhere. So we have more closed depressions in North American glaciated terrain than there are anywhere else. And that really contributes to our presence of the kind of closed depressions that are great for amphibians, vernal pools, and also sometimes create opportunities for local areas of ponding that might be the subject of our discussion today. So fun facts while we're waiting for everybody to log in today. How are we doing with login, Emily?
I think we're doing good. I'll just make a quick announcement. My name is Emily Vale. I'm the Executive Director of the Hudson River Watershed Alliance. We are really looking forward to our Toast to the Tribs coming up in a few months. That is scheduled for June 22nd. It's a Tuesday evening. We're going to be doing a live stream again. And the Toast to the Tribs is our annual awards benefit where we recognize the work of our Watershed Wavemaker awardees that have gone above and beyond to protect water resources in the Hudson Valley. And we're currently soliciting nominations for Watershed Wavemakers. So if you know of an individual, a watershed group, a business, an institution, an organization that has really gone above and beyond to protect watersheds in the Hudson Valley, please submit them as a Wavemaker nominee. We give priority to our volunteers, but are open to anyone. So I'm going to drop into the chat here the link to our Toast to the Tribs website, which has more information on the Wavemakers and how you submit those via email to me. And then if anyone is interested in sponsoring the Toast to the Tribs and supporting the Hudson River Watershed Alliance, there's more information on there along with all the benefits that sponsors receive. So thanks everyone for joining us this morning. I think we've got a critical mass here.
That's great. So,
and I should also say, sorry, we've got a couple Hudson River Watershed Alliance board members on this morning. Emily Svensson, Michael Finewood, and Dan Shapley are all here. I don't know if I missed anyone. If I did, you can let me know in the chat. And yeah, with that, I'll hand it over to Russell.
Yeah, I'm Russell Urban Mead. I was on the board for many years of the Watershed Alliance and absolutely delighted to work with Emily in coordinating these breakfasts. We were discussing before 8:30 this morning that someday we hope to return to the diner, but we don't know when we can do that because of the companionship and the sidebar meetings that are always such a valuable part of those conversations, not to mention the good breakfasts. But in any case, we're absolutely delighted to have Bernice Rosenzweig here today. We apologize for a schedule switch from last week, but I think you're going to be excited to hear what she has to say today. Apologies for me is that the week switch, I do have a 9 o'clock meeting. So after the kickoff here, I'm going to need to disappear. But that's the exciting breakfast presentation we have this morning. Dr. Rosenzweig is a faculty member at Sarah Lawrence College. She got her PhD at Princeton. Her specialties are focused on urban hydrology and climate change resistance, spectacularly focused relative to the interests of the Watershed Alliance in our audience. Bernice, for your interest, the kinds of people who are in your audience today are planning board members, zoning board members, very interested activists as individuals, many participants from a wide range of watershed type organizations, a real force of interested advocates and thinkers who appreciate understanding the science behind policy so that we can all be a force for keeping our eyes open and moving the ball in the right direction across the watershed. So your input today to all of us is very valuable. I'm seeing from your website that your focus, Bernice, is green stormwater infrastructure, adaptation to extreme rain, pluvial flooding, which I needed to look up, but that led me to the issue of the closed depressions. It's surface water flooding, and maybe you will say more about that, that is not directly associated with a river or a pond. And ecosystem-based nitrogen regulation. So we're delighted to have you here today. The time is yours here between now and 9:30. Just to say, I think what Emily already said, for those of you who have questions in the audience, please put them in the chat box, right, Emily?
We're going to use the Q&A box.
The Q&A box. And then when we,
a little more organized.
Very nice, in the Q&A box. And then when the presentation ends, and we usually have the presentation end maybe 10 minutes before the half hour, then Emily will troll through them, consolidate them, and feed the questions to you in the remaining 10 minutes, and we'll answer as many of it as we have time for. So thank you very much. Look forward to the talk. Thank you all for tuning into the Watershed Alliance Breakfast, and here we go.
Hi, yes, thanks so much. Can you all see my slides all right?
Yes.
Great. So thank you for the really nice introduction. And so today I'm going to give an overview of some of my work related to urban stormwater and how we can prepare for the projected impacts of climate change. And so just to kind of give an outline of what I'm going to cover, I'm going to start off with framing the problem, really the issue of stationarity and how climate change will result in non-stationarities to the weather patterns that we rely on. I'm also going to talk a lot about cloudbursts. And that's another term where, you may have to look it up. It's not that commonly used, but when the international community that's doing work related to urban stormwater resilience, it's a term that's increasingly being used. I'm going to talk about some of our initial research in terms of developing knowledge systems for cities to adapt their stormwater infrastructure for climate change, as well as some initial terrain analysis work that we've been doing and the importance of terrain analysis. So I really appreciated Russell's introduction. And finally, I'm going to talk about opportunities for next steps. So, we all know that the Hudson River Estuary faces important challenges as a result of climate change, both the climate change that's locked in and the climate change that will accelerate with increased anthropogenic emissions that are projected if we don't do something in the near future. So obviously we experienced post-tropical storm Sandy in 2012, which caused catastrophic flooding, not just in New York City, but a surge that propagated up the Hudson River. A year before that, we experienced extreme precipitation from Hurricane Irene, which caused river flooding. And we use these types of events really as analogs for what we have to prepare for with climate change. And obviously they're really important. But a lot of the work that I'm going to talk about related to stormwater infrastructure was actually inspired by a project that I worked on for several years. And this is the Urban Resilience to Extreme Sustainability Research Network, where we're obviously interested in resilience in cities, resilience to extreme meteorological events and climate change. And we adapted the view of cities as social eco-technical systems. So this was a novel approach where, instead of just thinking about infrastructure or thinking about ecosystems and green infrastructure or thinking about social problems in our usual stovepiped way, this is an opportunity for many of us to come together and collaborate. There were 13 institutions that participated in this project located around the Americas. We focused on 11 cities, and there were over 100 researchers that were participating as part of this project. And we adopted this working definition of resilience. I know that's something that's still openly being discussed, as the ability of an urban system and all of its constituent socio-eco and social technical networks across temporal and spatial scales to maintain or rapidly return to desired functions in the face of a disturbance, to adapt to change, and to quickly transform systems that limit current or future adaptive capacity. So the disturbance that my work focused on as part of this project was obviously the disturbances that would lead to urban flooding, and to think about how these cities could begin to learn from each other to prevent flooding from happening and to adapt to it and quickly recover from it when it did. When we began this project, we initially expected to focus on the type of flooding that we all think about that when we think about climate change. So flooding as a result of tropical storms and hurricanes and other coastal storms that result in storm surge flooding or river flooding as a result of extreme precipitation. And so what I found, and my work, I'm sorry I didn't introduce this, my work is primarily going to focus on Baltimore and New York City, obviously, although I'll give some examples from the full network. What we found is that while we were expecting, to focus on coastal flooding and fluvial flooding, or river and stream flooding, which is what we normally think about, where you have a stream, it rises above its banks, and the adjacent floodplain is inundated. We found that most of the cities, we expected this type of flooding, like the flooding of the Jones Falls in Baltimore, and when we actually spoke to city practitioners and stakeholders, we found that they were telling us over and over again about these incidents that happened far away from our natural waterways, far away from stream corridors, far away from river corridors, outside the map floodplains. And they resulted from this mechanism that is increasingly being called pluvial flooding. Now, I hate that terminology too, because pluvial is obviously associated with rainfall, and this isn't flooding that's limited just to inland flooding from extreme rainfall, but specifically to the mechanism of flooding where precipitation exceeds the rates of infiltration and engineered drainage. So, we've in many cases completely replaced our natural waterways, our natural stream corridors with subterranean infrastructure. When those sewer networks are overwhelmed, when their design capacity is exceeded during extreme rainstorms, you get ponding and in some cases overland flow. In some cases, as I'll show you in some of our cities with topography, very high velocity overland flow that results in damaging flooding. And so when I talk about pluvial flooding, I'm really talking about this type of failure of our stormwater infrastructure, this specific mechanism of flooding. And so when we think about the evolution of our cities, cities have evolved from having open gutters to having the closed sewer system with wastewater treatment plants that we're all familiar with. And increasingly we're using green and gray infrastructure in tandem to really optimize the performance of our sewer system. But as we think about the evolution of our cities, it's important to keep in mind that whether we're thinking about gray infrastructure, whether we're thinking about green infrastructure, all are engineered based on a design storm. And in the case of our stormwater drainage system, those design storms are typically usually very modest. So the international standard is to design for the 10-year storm. There is no international standard duration, just that return interval. But since most of our cities were built, or the infrastructure in most of our cities were built well before those international standards were developed, in practice in our cities, our storm sewer networks were designed to manage storms with much smaller return intervals, often the 2 to 5 year storms. We're saved from having, flooding events, pluvial flooding events that occur really, really frequently because engineers usually also included some sort of factor of safety. But that factor of safety is variable. And we know that the performance of our infrastructure is also impacted by other factors like clogging and maintenance, in addition to overwhelming the design storm. One important thing that we also need to keep in mind is that design storms are identified based on weather records. So, we rely on our long record observations, like for example, the ASO station in Central Park. Um, and we use those observations of historic precipitation, obviously along with statistical relationships, to project the frequency of extreme rain events of various durations. And there are imperfections with that already. Our records don't go back very far. The Central Park station only goes back to the mid-19th century, and it's one of the longest record stations that we have in the area. But even so, we really are dependent on this idea of stationarity, that we can design our infrastructure based on the weather of the past. And with climate change, we can't rely on that assumption anymore. And so in many of our cities, we rely on historic records of precipitation that are actually already far out of date. They don't consider the potential effects of climate change. They were also, they haven't been updated in many years. So although we have much newer products, like for example, the NOAA Atlas 14 product that many of us might be familiar in our work, in practice, when we spoke to practitioners for a variety of reasons, they're still working with older precipitation record data. So for example, New York City still relies on TP25, which was released in 1955. So we're relying on weather records that, preceded the mid 20th century and really didn't represent the increases in precipitation that happened in the later part of the 20th century. We see the impacts of our reliance on these historic records day to day. So for example, I'm primarily going to be talking about flooding, but the same types of exceedances of, when our storm sewer systems and when our sanitary sewer systems are overwhelmed result in a lot of the water quality issues, or contribute to a lot of the water quality issues that we're concerned with in the Hudson River Estuary. So obviously in this region, we have quite a lot of combined sewers, which release untreated sewage along with stormwater into waterways during heavy rainstorms. But even in some of the cities that we studied where there are separate sewer systems, this type of overwhelming of our stormwater and sewer infrastructure together can cause water quality issues. So Baltimore actually has what's technically a separate sewer system. It's got one of the oldest separate sewer systems in the country. But because of infiltration of stormwater into their sanitary sewers during heavy rain events, they have had thousands of basement backups in the past decades, which has resulted in millions of dollars of damages in that city. And there are lessons to be learned as we think about planning our sewer system upgrades in our city, even though we're primarily thinking about separating the system. That's not always going to be the panacea for the problems. So I just want to give a case study of an example of when our stormwater system is overwhelmed and the impacts that can occur. So one recent example happened in July of 2019 in New York City. And so here are some of the examples of the flooding that occurred throughout the city, primarily in Brooklyn and Queens. This storm resulted from several days of high pressure offshore. It was very hot and humid, and then a cold front moved through the region during the evening of July 21st. Following that, a wave of low pressure moved along the cold front in the late afternoon of July 22nd, and this was all very well forecast. So there were warnings, flash flood warnings issued by the National Weather Service more than 48 hours in advance. And they predicted a basin average rainfall of 1.5 to 2 inches of rain. So we don't really have distributed measurements of precipitation throughout the city, which is one of the big challenges we face. We can take advantage of products such as, for example, NOAA's quantitative precipitation estimates that are radar-based to try to estimate what precipitation fell during these types of events. And here's just an example of the 3-hour accumulation associated with this July 22nd cloudburst. You can see that the National Weather Service forecast was questionably pretty good. In the 3-hour accumulation, you can see there was a swath of the city that received close to 3 inches of precipitation total. A lot of that fell in a little bit more than an hour. And you can see that there were street flooding complaints that were associated with this event that kind of fell along the axis of the heaviest rainfall, but also occurred outside the axis of where there were the greatest accumulations. And so this is just a quick animation showing the NOAA weather radar's quantitative precipitation estimations. This is an estimate, it's really tricky, especially with these more intense events, to actually accurately estimate what precipitation accumulations were. But you can see that in addition to having these areas where there were heavy rainfall accumulations, I'm sorry, just gonna go back and play the animation again. A lot of the street flooding that was occurred in places that might not have had relatively high accumulations, but experienced very intense rainfall. So in the vicinity of Jamaica Bay. And so these are precipitation events where the heaviest rainfall falls over extremely short time scales. It's not just sub-daily, we're talking sub-hourly. Intense rainfall that occurs in 15-minute intervals, for example. And it's really challenging to figure out how we can design our infrastructure to manage these types of events in some sort of cost-effective manner. Just to try to provide some context for this case study event that I'm describing, you think about the intensity, duration curves that are provided by TP25. So this is the historic weather-based guidance that New York City still uses to design its infrastructure. And so what I'm showing you here, these types of diagrams, if you're not familiar with them, I'm showing the duration of rainfall on the x-axis, and I'm showing the associated intensity of rainfall over that duration on the y-axis. And so if you were going to think about how much rain based on the radar estimates fell in 1 hour, this particular event wasn't that extreme. It would be expected with a return interval of less than 5 years. You consider the 3-hour interval, this sort of event was associated with the return interval of about 5 years. Yet it still caused the flooding that I showed you in those pictures and disruptions throughout the city. This type of chronic flooding is generally assumed to be a nuisance, but it can pose important public health threats. So in parts of the cities that we experience this flooding every few years, there are issues of mold and mildew in basement. There's potential exposure to sewage pathogens when stormwater is combined with sanitary flows. And there are also impacts to public health related to the stress of constantly having your property flooded. But while the case study that I showed you is an example of one of these more frequently occurring nuisance events, we found some examples based on our literature review and our records review of these types of pluvial flood events that resulted in life-threatening conditions. So for example, here's a flooding event that happened just a few weeks later in the city of Baltimore, where the neighborhoods of Canton and Fells Point experienced pluvial flooding. And you can see that, for example, this gentleman needed to be rescued from his car because the water was very deep and fast moving during this particular cloudburst event. And I'll come back to this event in a little bit. And so, we have this kind of overview of what a frequently occurring cloudburst event will do in terms of its overwhelming of our storm sewer infrastructure. As part of our research for the urban resilience to extreme events, we decided to do a little bit of a review of the US National Center for Environmental Information's storm events database. And so this database provides narrative records of significant meteorological events. For tornadoes, it goes back actually to the 1950s. For other types of events, it goes back to 1996. And we synthesized all the records from this data set for our UREX SRN cities that were located in the United States. And what we found was really surprising. We found many examples of severe pluvial flooding in New York City. So we usually think about this type of flooding of being a nuisance event, like in the July 2019 case study that I showed you from New York City. But there have been events in New York City, for example, one incident in 1999 in Queens that resulted in life-threatening flash flooding where people were literally, in their homes, in their basement residence with water up to their necks and had to be rescued. In the city of Syracuse in 2011, a man was swept to his death during pluvial flooding event. And in Phoenix, there was a recent event associated with the monsoon where hundreds of cars were stranded throughout the Phoenix area, many buried to the tops of their hoods, and people had to be rescued because they faced life-threatening conditions. One event that we were particularly interested, that we first identified through this database, was a severe pluvial flooding event in Baltimore. And so this was event 5370066 in the NCEI database. And here are some of the descriptions of what people experienced that were considered reliable to make it into the database. And it was described that 2 streets became rushing rapids, washing several cars hundreds of yards away, that motorists had to be rescued from their cars or had to be swim or to some safety. What's really alarming was that they described walls of water in 2 locations. And you can see the locations of those where these events were described to have occurred, that reached a height of 3 meters at these intersections, and that numerous homes were damaged and 1 woman was injured. And so if you look at the location of where these incidents were reported, and so I'm showing in this map the topography, but I hope that you can see in the way that my slide is presenting colors that there's a light blue shaded area that refers to the 500-year floodplain. And so you can see that both of these incidents were recorded nowhere near the currently implemented 500-year floodplain, obviously well outside the regulated 100-year floodplain. But here's an example of where pluvial flooding resulted in severe life-threatening impacts. And our policies really just don't have any mechanisms for addressing this at this point. Pluvial flooding is, for all intents and purposes, excluded from FEMA's floodplain mapping. So usually when we do floodplain mapping, we identify surface water bodies. We map transects. We use that transect data in models like HECRAS, although others are approved. And EPA SWIM is improved for use for floodplain mapping, but in practice, it's rarely utilized. The big issue is that most of our flood insurance studies are based on identified surface waterways, and we've replaced our surface waterways functionally with sewer systems. Our cities are stream deserts, which is a term one researcher has begun to use to identify them. So we're not really mapping this pluvial flood hazard in practice in our US cities. And part of the reason is that there's an assumption that overland flow will generally just be a nuisance, that it will remain less than 1 foot. And that we can just use engineering judgment for the sheet flow. And some cities actually do that, like for example, Phoenix does it because of its topography and climate. But in practice, we've identified where these events are happening frequently, and their frequency is causing many problems for urban residents. We've also identified these incidents where there was severe and life-threatening flooding that's just not considered in our national flood insurance program. So as part of our research, we've been really interested in developing methods for pluvial flood hazard assessment, sort of as a complement for FEMA's National Flood Insurance Program mapping. And we know how to do this technologically. We have fully coupled hydrodynamic models that can consider infiltration, the storm sewer network hydraulics, and stream flow modeled, and overland flow. Couple them together, we have increasing computational resources. There are a variety of over-the-shelf packages that can be purchased to do this. But yet in practice, we don't do this. This isn't the way that we're doing our current flood hazard mapping. That's for a variety of reasons. So a bunch of my collaborators and I recently wrote a commentary in Earth's Future about the potential value of doing this type of urban flood modeling, where we discussed many of the barriers to implementation. But when you think about it, one of the largest barriers is that in our existing cities, our sewer systems are over 100, in some cases nearly 200 years old. And we just don't have reliable data on where our storm sewers are located and how they're operating. When we do have data that's reliable, and no city's data is perfect, even for example, New York City's data has gaps because of the age of its system. The data are often inaccessible to researchers due to security and liabilities concerns. And the licenses for these models are often prohibitively expensive. We can build them from scratch, but that's a project in its own right, and it's really reinventing the wheel. And despite our advances in computational resources, this type of work is still really extremely computationally expensive. So if we want to run multiple scenarios, we really need to have access to supercomputer resources, which most researchers and definitely most cities just don't have. And so thinking about climate change, we know that this issue of short duration rainfall events is already a problem for our stormwater infrastructure. We also know, although precipitation forecasts remain very uncertain, one thing that we're certain about is just from basic thermodynamics, these types of short duration intense events are the ones that are certainly going to increase as the planet continues to warm. And so, we can think about the Clausius-Clapeyron relation, which is used in one way to represent how atmospheric moisture or the potential saturation atmospheric moisture increases with temperature. And so if you just use, a linearized form of the Clausius-Clapeyron equation, and you consider what would happen locally in our various cities if on any given day for any given event it was 5 degrees warmer. Now I'm not talking about the global average temperature, I'm talking about the local temperature that experienced in any given place. What is now an infrequent event, what is now an extreme event, is going to become a regular event. So if you think about the design of our storm sewer infrastructure, what is now the event that would occur with the frequency of 10 years now, if we think about the effects of warming temperature on atmospheric moisture, we can expect, for example, in New York City, what the type of rain event that would occur with a 40-year return interval could be expected as frequently as every 10 years. So that's important to consider, when we think about our infrastructure and we think about our vulnerabilities to climate change. Our infrastructure can't handle these currently occurring cloudburst events, and we know that as the planet warms, they're going to occur more frequently. And so, we've got this process where warmer temperatures result in increased atmospheric moisture, with all other things being equal. But unfortunately, all other things are not going to be equal. As temperatures warm, they also result in increased convection. So we'll have more intense storms that will further amplify precipitation. And this will all be going on at the same time in coastal cities like along the Hudson River as sea levels are rising. And so that those increased sea levels will further impact the performance of our stormwater infrastructure. As sea levels rise, it can rise directly above the level of our storm sewer system outlets, resulting in decreased capacity of those systems to convey stormwater during intense rainfall events. As sea levels rise, groundwater will also rise in tandem, resulting in increased infiltration into our storm sewer and sanitary systems. And as I showed you from the example in Baltimore, infiltration of groundwater, particularly during wet weather events, plays an important role in the function of our sewer system and really decreases the function of our sewer system and can result in backups. So all of these things will be going on at once. And this is what we have to think about when we're thinking about stormwater resilience. But although we know that these processes are going to increase both in frequency and magnitude, we don't have the technology to quantify how they're going to increase, irrespective of human scenarios of how we will increase emissions or pathways of increased emissions or reductions. But for any pathway of emissions, there's quite a lot of uncertainty in how that will translate into quantitative precipitation that we can use as the basis of our infrastructure design. There's really going to be no new normal for engineers for design for. And that's an incredible challenge. We can describe that as one of these wicked problems that we face. And so going back to this issue of how we can do pluvial flood hazard screening under these circumstances, we can think about a really big picture approach where we consider how the water cycle functions during these short duration events. And if you think about the urban water cycle, overland flow, the flooding that we want to prevent, results from precipitation, which is going to increase. and is mitigated by regulatory processes like evapotranspiration, infiltration, storage, and obviously the conveyance of our sewer system. And our design of green infrastructure has focused on enhancing evapotranspiration and infiltration, and to a lesser extent with storage of stormwater, and all of the benefits that that provides for us in terms of improving water quality and reducing strain on our sewer systems. But during these intense rainfall events, these cloudburst events, when you think about it, the performance of our sewer systems is obviously negligible relative to the rate of precipitation, but the rates of evapotranspiration and infiltration are also functionally negligible at short time scales. So we have to think about other approaches, and that really becomes down to storage, how we can think about designing our landscapes to enhance storage. And for this purpose of screening, where stormwater will be unintentionally stored on the landscape, resulting in flooding. And so our workflow for this type of terrain analysis is actually really straightforward. We have in many of our cities, and this is becoming increasingly available, really high resolution, high quality digital elevation models. And so those models at present really represent the bare earth surface. We know as cities become denser, like for example, in New York City, the bare earth surface really isn't representative of where water is going to flow over land. And so our initial DEM preparation work was your typical hydrologic conditioning. We did not fill pits because the pits are what we're interested in this case, for those of you that have done this type of hydrological conditioning work. But correcting for, making an assumption about whether buildings are completely permeable or completely impermeable for various scenarios, correcting for conveyances under trestles and around infrastructure like that. And then once the DEM is prepared, we would develop some sort of precipitation scenario. For these types of initial terrain analysis screenings, we assumed uniform rainfall, although we know that's not the case. And we can run scenarios where we consider uniform rainfall and subtract the potential sewer design conveyance, because we know that we have these gaps in our sewer system performance, or that the data are simply unavailable. And then in terms of our terrain analysis, we use hierarchical filling and spilling. So we basically just route water over land, over the surface, because we're assuming at these time scales that subterranean processes are negligible. We fill the pits that we're interested as appropriate during the course of the events, and we allow spilling over the pits when they're inundated. And using this process, we can identify areas where potential deep inundation can occur, and identify the associated surface flow catchments of those deep inundation areas. And so we've gotten some interesting results from this type of work. These are most of the terrain analysis that we've done so far has been in Baltimore, and in New York. Our current work focuses on integrating using the LiDAR point cloud directly, as well as New York's 3D building model to develop a better surface model for doing this type of work. But in Baltimore, which is less densely built out, we've been working primarily from the digital elevation model. In this case, making assumptions about the permeability of buildings. We used the uniform assumption that they were partially permeable, and running our hierarchical spill fill model. And you can see in our initial results, we got some interesting results where we can see that there was obviously, based just on the topography, inundation in some areas that are known to be flood prone. So for example, in Fells Point at the intersection of Caroline Street and Alisana, which floods very frequently, but often doesn't flood to any extreme depth, you could expect about a foot or of stormwater to inundate that intersection. And just from the topography, if the storm sewer has been overwhelmed. We could also identify areas that would allow for the accumulation of deeper water, like for example, this underpass that I'm showing you, where a woman had to be rescued from her car. The problem is there's no consistent or standardized approach for validating these methods. We really don't have good data on when this flooding occurs and where it occurs, where it's transient. And so we're relying on alternative methods, like for example, this woman that was rescued from her car in this underpass was live Facebooking her rescue and taking photos. But if we didn't have these social media reports, these contributions from the public, we really wouldn't have any consistent record that these events were happening outside of like narrative reports, like I showed you from the NCEI database. If you go back to the event that I told you about on June 13th, 2003, where there was that catastrophic flooding, not surprisingly, if you just look at the topography and hierarchical flow spilling, you can see that these locations are sites where water can really accumulate at depth. And you can see how this description of a 3-meter wall of water could have been feasible, just in terms of how much water would accumulate in these catchments. So one interesting event that happened also in Baltimore recently, I had an undergraduate student that was working on mapping historic stream channels that had been buried in the city of Baltimore. We were focused on the historic Hartford Run, which no longer exists, but was filled in the early 19th century. And so this is the present day surface catchment of Hartford Run. I'm not sure if you can see my cursor, but it's outlined in white in my image here. And on August 6, 2019, they had a really extreme cloudburst that occurred, really focused right over this catchment, or this storm sewer catchment that we had been studying. And you can see that there was very, very heavy rainfall rates that just continued to train over this part of Baltimore. The storm total rainfall were, very short period of time, was up, in some places just east of the catchment that we were studying, over 4 inches, in the catchment that we were studying on average about 3 inches. And so this is associated with a 100-year, 1-hour storm, or 1-hour precipitation event, more or less, for the city of Baltimore, based on the NOAA Atlas 14 records. And so, you can just see the duration of this event was really short. We're talking less than 2 hours, with the most extreme precipitation falling within 1 hour duration. And so if you look at the superficial flow paths and you look at where water will accumulate, this is just the result of some of our terrain analysis modeling. You can see that there are some places that are natural features within the landscape. So for example, ponds where water will accumulate. You can see that there are some places where there are remaining topographic depressions where water will accumulate. We don't have data distributed throughout this catchment about whether inundation happened in all these areas. But we do know that, just by analyzing the topography, that we can identify areas where water can potentially accumulate. And so, for example, I showed you that photo where this man had to be rescued from his car. That intersection was an area where under these extreme rainfall conditions, if you don't have the function of surface flow path, of subterranean flow pathways, water can accumulate at depth. So we've got this ongoing challenge of how cities can afford, the needed, what would be billions of dollars, literally, of rapid upgrades to their sewer system to account for these increased extreme rainfall events. So we were interested in working with cities to learn more about how they plan for these events. And so we considered the case of Phoenix, which is a really interesting case because it's a desert city where they actually design, their sewer network only is designed for the contemporary 2-year storm, and they actually design for overland flow on streets up to the contemporary 10-year storm. In some cases, they actually, although this is not a practice that they have anymore because it was too hard to maintain, they actually have reverse crown streets where the actual street grading is designed to more rapidly convey water over land. And the idea is that you have your extreme rain events. Everyone would just not drive on the streets. And once the cloudburst has passed, then you can just resume business as usual. They also use green infrastructure designed for the 100-year storms for new development. But when you exceed the design capacity of this green and gray infrastructure, really their only strategy is social, to rescue. There's no plan. And a lot of these flooding impacts are not covered by our existing social mechanisms like insurance, and the burden is really faced on private property owners. We also considered, for example, New York City's plan for dealing with these types of cloudburst events. And New York City learned a lot from the city of Copenhagen, Denmark, which wasn't one of our study cities, but has emerged as a real leader in cloudburst management. And so Copenhagen experienced a cloudburst in 2011 that resulted in catastrophic flooding, and they've been really working to upgrade their stormwater infrastructure ever since. Their storm sewer system is designed to convey the 10-year storm, but they're piloting these cloudburst boulevards, which, like the Phoenix reverse crown streets, are designed to support the infiltration of stormwater during moderate rain events and convey stormwater like a stream during more intense cloudburst events. They're also thinking about urban landscaping and how they can design their parks thinking about overland flow to support large-scale stormwater detention during the 100-year storm. And they're thinking about how the 100-year storm might be amplified with climate change. So a lot of this cloudburst infrastructure that I'm describing is designed considering future increases based, in the case of Copenhagen, on downscale climate projections. This more green cloudburst infrastructure is being used in tandem with gray infrastructure. So they're building large scale tunnels in the densest areas of their cities to convey amplified rainstorms. And so New York City has used Copenhagen as a model and is piloting some of this type of cloudburst infrastructure, particularly in Southeast Queens, which is a really flood-prone part of the city. And so that includes gray infrastructure, which is designed for the contemporary 5-year storms in tandem with our green infrastructure plan, which is designed as under the consent decree for water quality protection. But they're now piloting green infrastructure design with cloudbursts in mind, to prevent flooding in addition to providing water quality benefit. So this includes on-site stormwater storage and retention at public housing projects. There's a pilot housing project in Queens that they've got a design for and they're hoping to construct very soon. This includes cloudburst roads, which will convey stormwater during the 10-year storm with considering future climate change. So we know that's kind of the equivalent to the 40 or 50-year storm today. And they're also developed a master plan where these types of cloudburst infrastructure would be implemented throughout the storm sewer shed. And that's something that still, it hasn't been piloted yet, but it's something that they hope to do a pilot implementation of in the future. We're considering, designing for the 100-year storm in 2115. So with the increases in extreme precipitation that are associated with climate change. And so this type of cloudburst design really adopts what's being called a 3 points approach. This terminology really hasn't caught on in the United States, but it's being widely used in cities like Copenhagen and throughout Europe, where they've begun to think about how they're going to adapt their storm sewer system to the amplification that we expect due to climate change. And they identified 3 domains of management, these 3 points. And so the first is the way that we already design. We design for a design storm. And the idea is optimizing our sewer systems, optimizing our drainage, optimizing also our green infrastructure systems for this design rainstorm. We don't yet design for extreme events, but that's the second point that has to be considered. And so when we talk about the 3 points approach, the idea is that you have to design for all 3 approaches at once. But surprisingly, the third approach is really important for making design for the first 2 points of management, the design storm and extreme rainfalls that exceed the design storm, feasible. We know that it's prohibitively costly to just upgrade our storm sewer system, although we've got this challenge where we really have to. And so the idea is that you can use co-benefits or the performance and the function of this type of infrastructure during dry conditions to try to offset those costs. And we already do that to some extent with our green infrastructure. The idea is that we can do this at larger scale. So for example, large scale detention that serves as a park under normal conditions, large scale grayer detention that serves, for example, as an amphitheater or basketball court that's submerged under dry conditions. And that's our third domain of management that has to be considered. And that's where, ecosystem services like infiltration and evapotranspiration are still really important. So I really want to emphasize this isn't an issue of green versus gray. It's more important to think about the different points of management, how they will function, how our infrastructure will function under these different conditions. Infiltration still plays a role during our design storm along with sewer drainage. But in our third point of management, it's really thinking about how you manage our landscapes, how you manage our topography as a whole, and how we can think about that holistically in terms of how our city functions. So just to wrap up, and I hope that we have some time for questions and discussions. Cities are already vulnerable to flooding caused by cloudbursts. And in our older city, even moderate cloudburst events can cause severe impacts. We know that climate change is going to increase the frequency and magnitudes of these types of cloudburst events. We have to think beyond green and gray and to really adopt this 3 points approach for management. So the next steps for my research is going to be to continue this type of terrain analysis, linking flood hazard screening with opportunities for landscape design. But I hope that this has been interesting, and I really welcome your questions and a discussion as we have time about these challenges and potential opportunities. So thank you.
Great. Thank you so much, Bernice. Your research hits some of my favorite topics. I'm really thrilled that you could be here this morning. So we've got a lot of really great questions. And I wanted to start with this question of collecting information on these cloudbursts and pluvial floods. Do any citizen science crowdsourcing apps or data collection programs exist? Is there a need to develop something like that to capture this important information?
Yeah, so there are quite a few. And so first off, this isn't what we typically think about as citizen science. It's more crowdsourcing. But in New York City and in many other cities, you can report various types of flooding, street flooding, basement flooding, clogged catch basements and related issues through their 311 system. And those 311 data are publicly available. And we've been exploring how they can be utilized to identify areas that are experiencing chronic flooding. Where there are some challenges in utilizing that data, in that not all communities use the 311 system consistently. And in some cities that are already more vulnerable because of social reasons, they're less likely to report flooding when it occurs. It also is less representative of the more severe impacts of flooding. So, although we had that incident with the woman was Facebooking her rescue, if you're in danger, you're often not going to call 311. You shouldn't be calling 311. So it's limited in that way. There are programs that are being implemented. So Aditi Bhaskar at Colorado State University has implemented a citizen science platform called Flood Tracker that can be used to report street flooding. The challenge is really developing a user base for it. And there are limitations, for example, in community use of technology, but there are also concerns about making this data publicly available. If you're a property owner in a place that experiences chronic flooding, you might not want to report that your neighborhood is frequently flooding. You might not want that data to become used by, for example, the real estate community, because it will lower your property values. So these are all challenges for citizen science and crowdsourcing, although we know that that's going to play an important role in monitoring these types of events when they occur.
Great, thank you. In terms of the locations of these pluvial flood events, are there any correlations that you found with environmental justice areas, mapped red line areas? Are these residential versus commercial or industry? Thinking about some of these social factors.
We are going to do that kind of work rigorously this summer. So that's actually, I've got funding to actually do that type of work, where we, look at the relationship between where chronic flooding is occurring and these other environmental justice issues. So I can't say quantitatively whether that's the case yet, but it's something that we definitely hope to explore. But one of the challenges in doing that type of work is we can do that based on the topography. So we can predict which areas are going to be more vulnerable to this flood hazard just based on their topography if the infrastructure fails. But in considering environmental justice, we have to consider the limitations that we have in where flooding is reported. The environmental justice communities are the ones that are less likely to report flooding. And so, we want to be careful about using, those data sets alone to identify the problem, because we know that there are these limitations. It's one of the reasons, a primary reason that this issue hasn't received as much attention as it deserves. These events just are hard to quantify when they occur.
Right. Got two different questions here about storage related to cisterns. If you can speak to feasibility of using rain barrels or cisterns to capture stormwater runoff in urban areas in particular, or case studies?
Yeah, so any storage helps, right? But it's quite a lot of storage that you have to provide. So that would be quite a lot of cisterns. And so, for example, the New York City Department of Environmental Protection has their pilot rain barrel program where they're, broadly implemented rain barrels. They've distributed tens of thousands of rain barrels, and they do reduce, slightly reduce the volume burden on the sewer network during extreme rain events. But if you think about the really extreme events and you think about just how much volume you have to manage over a short period of time, the cisterns can only play a small contributory role. We really need large scale storage at the scale of landscapes.
Okay, great. And okay, that's a good transition. We have a question. The large scale detention that serves as a park, can you share any specific case studies or examples of this being successfully done?
So this is still being piloted. And so there are examples in Copenhagen where they're designing their parks specifically for cloudbursts. There are other areas throughout the world where they've designed parks to manage stormwater and reduce the burden on the sewer system for water quality improvement. But in Copenhagen, they're designing parks specifically for cloudbursts. Thing is, this landscaping was done very recently, and so in terms of how it will actually perform, there hasn't been an event yet. But that's something that we have ideas about how this will work for moderately extreme events like the 100-year storms, which they're designed for. And we'll see how they function in practice over the next couple of decades. Not quite a park, but New York City St. Albans plan would essentially use the green spaces in public housing projects to provide amenities for the residents, like, for example, urban gardening, which would then be inundated and provide large-scale storage for the entire sewer shed during a storm event. I mean, they're at the design phase there, that it hasn't been built yet, but that's something that will be piloted in the next few years.
Great. So you mentioned this term stream deserts, that cities don't have streams, they've been incorporated into the sewer systems. Would daylighting help with storage, or in other ways helping handling the cloudburst events?
Yeah, so it depends on how the daylighting is done, though. I mean, here's our opportunity to provide enhanced conveyance with better floodplain management. And we can restore the function of our watersheds and allow it to better manage the conveyance of water during these extreme cloudburst events. The problem becomes in our densest cities where cloudbursts present the most risk, that there's no space. That daylighting would involve displacing existing residences and existing infrastructure. And so that's the real challenge. We've already built over our natural water courses. These are the areas that in some cases, and this is the project that we're working on in terms of historic streams in Baltimore, and also we're hoping to begin this work in the Hudson Valley, that are topographically more vulnerable to flooding, because that's where the topography still has this legacy of where the streams occurred, and these areas are getting flooded. But then it's not necessarily feasible to perform that daylighting in those areas because we've already built there and people are living there, and you'd have all the problems associated with displacement.
Great, and we know it's 9:30. We're going to have one more question. Sorry we couldn't get to everyone's questions. Is the terrain analysis mapping publicly available for planning and design purposes? If not, is there a plan to make it publicly available?
Not yet, because so the work that we're doing in Baltimore, we're hoping to publish. It should have actually been published this winter because we're very close to being finished, but I've been extremely tied up with teaching and getting used to my new position. So we're going to finish that up this summer and then submit that. Once it's published, then the data will be publicly available.
Great. Okay. Well, thank you so much, Bernice, for this fascinating talk. You've given us a lot of food for thought, and I think there might be some opportunities in our slightly less dense Hudson Valley cities and villages where we might be able to implement some of these best practices going forward. So,
yeah, and it's really exciting to think about. Although, we can't necessarily do full-scale stream daylighting areas. There are examples, like, for example, the Sawmill River Daylighting Project, where we can do partial daylighting or create water features and other ecological amenities while also designing to manage for these cloudburst events. So I'm just gonna put my email in the chat. If anyone has questions, I'd be happy to answer them by email.
Okay, perfect. And I'll be sending out a link to this recording, and I'll include Bernice's contact information as well if you have additional questions that we didn't get to. So thank you very much, everyone, for joining us this morning. Thank you, Bernice, for sharing this fascinating information. We look forward to seeing everyone next month for our next breakfast lecture in May, on the second Thursday of the month.
And thank you so much. And I look forward to meeting many of you in person as soon as it's safe enough.
Wonderful. Take care.